All right, so we're looking at section 7.1 on page 407, looking at inverse functions. The majority of this is Algebra 1. We don't really run into any calculus until we get to the end of the lesson. We have a theorem at the end of the lesson that we work with. So to begin with, they taught to us in the very beginning a little bit about functions and inverse functions. Remember that with a function, you can have no two x values that are the same. And an easy way to test whether the function that you have is, or whether the equation that you have is a function or not, is to graph it and do the vertical line test. If you go through, like let's say example number 2, we've got this parabola. If I go through and I do the vertical line test, that means that I go through and I draw vertical lines and I make sure that I hit the graph in no more than one spot. If I hit my graph in more than one spot, what that identifies is two x values that are the same. Because if you think about it, if, like, let's say right here, this is x is equal to 1. If I were to hit my graph again up here somewhere, that's still x is equal to 1. It would be a different y value, but that would be two x values that are the same. That's what the vertical line test looks for. All right? Then they talk to us about an inverse, and they tell me that a function's inverse is also a function if it has no two x values the same. So an easy way to test that, instead of me having to sit here and draw the inverse of this function and then do a vertical line test on it, if I want to make sure that there are no two x values the same on my inverse, remember that for an inverse function, you switch x and y, right? So if I want to make sure there are no two x values the same on the inverse, that means there could be no two y values the same on the original, right? Let me say that one more time. Because for an inverse, x and y switch places. If I want no two x values the same on my inverse, that means there can be no two y values the same on my original. So an easy way to check for that is the horizontal line test. And so that's why we said if you want to check if your inverse is a function, make sure that your original function has no two y values that are the same by doing the horizontal line test. And so again, going back to example number 2, this parabola, when I do a horizontal line test, it fails because I hit the graph in more than one spot. So that means that there are two y values the same on my original. That would be two x values the same on my inverse. So my inverse would not be a function. So example number 2 is a function, but its inverse is not a function. All right, look at example number 1. For example number 1, if I go through and I do the vertical line test, it passes the vertical line test. So yes, it's a function. It also passes the horizontal line test, so that means, yes, its inverse is also a function. So when the function and the inverse is also a function, we call that a one-to-one function. So when both the original and the inverse are both functions, we call that a one-to-one function. So sometimes they'll ask me to test whether it's one-to-one. Easiest way to do that is horizontal and vertical line test. Now, the notation that we typically use for inverse looks like this, f to the negative 1 of x. Now, I know negative exponents tell us to move below the division bar. They're not talking about a negative exponent here. They're talking about inverse notation. So they'll try to be very careful in the homework and in the notes and in the examples to specify to us when they're talking about inverse so we don't accidentally think that they're talking about a negative exponent. All right, so look at example number 3. For example number 3, they tell me if f of 1 is equal to 5, and f of 3 is equal to 7, and f of 8 is equal to negative 10, then what does the inverse of f at 7 mean? All right, now we said a moment ago that when you're working with inverses, x and y switch places, right? So if on the original function I have the ordered pair 1, 5, what would the inverse ordered pair be? 5, 1. So down here, when they're asking me what's the inverse of 7, we can come right back here and say, okay, if the original ordered pair was 3, 7, then the inverse ordered pair would be 7, 3. Exactly. All right, so what's the inverse of 5 going to be? And what's the inverse of negative 10 going to be? 8. Perfect. The next thing that they talked to me about is how to find the inverse of a function. Instead of just finding a particular value, maybe I want to find the inverse of the whole equation. And some of them are very logical. I mean, it's just common sense that I can utilize to figure it out. So, like the first one, we've got f of x is equal to x cubed. So what's the inverse of cubing something?
Cube root.
Cube root, right. So its inverse would be the cube root of x. And we used common sense to figure that out, but you might remember that last year in pre-cal, and probably before that in algebra as well, you had a way of proving that two functions were inverses of each other. And that was by doing a composition of those two functions. If two functions genuinely are inverses, they should undo each other, right? I mean, inverses undo each other and take you back to what you started with. Like if you start with x and you add 2 and then you subtract 2, you go right back to what you started with, just that plain x, because adding 2 and subtracting 2 are inverses. So on the bottom of page 409, they call them cancellation equations. Last year we called them basically the algebraic proof that two functions were inverses, and that is you should be able to take the function of the inverse, a composition of those two functions. They should cancel each other out and just take you back to x. Similarly, you should be able to do the inverse of the function, and they should cancel each other out and just take you back to x. So they're calling them cancellation equations here. We called them the proofs, algebraic proofs of inverses last year. So we think that this is the inverse of x cubed. Let's test it. Let's come over here and let's do f of the inverse. So I'm going to start by replacing the inverse with what it's equal to, and that's the cube root of x. So all I've done is replace the inverse of x with what it's equal to, the cube root of x. So now I have f of the cube root of x. What does that tell me to do?
Plug in the cube root of x.
Put in the cube root of x in the place of x, right, in the f function. So if I come over here to my original f function, I'm going to put the cube root of x right there in the place of x. So that would be the cube root of x cubed. So that's what we're going to have over here, the cube root of x cubed. And of course, the cube root and the cube cancel each other out and just give me x. All right, let's go the opposite way with the composition. We're going to do the inverse of f of x. So let's replace f of x with what it's equal to, which is x cubed. So now I have the inverse of x cubed. What does that tell me to do? Yes, put x cubed in the place of x in the inverse. So over here, our inverse equation, we're going to put x cubed in the place of that x. So that would give us the cube root of x cubed. And again, the cube root and the cube cancel each other out and just give me x. So those are our cancellation equations. Sometimes when I'm working with an equation and I'm trying to find the inverse, it's not that obvious. Like for the next example, example number 4, we've got f of x is equal to x cubed plus 2, and they asked me to find the inverse. Okay, well, what's going to undo cubing something? Cube root. And what's going to undo adding 2? Subtracting 2. So I have the general idea of what I need to do, but I may not know which order to do it in. Like, do I subtract 2 first and then take the cube root, or do the cube root first and then subtract? And of course, when we start working with, trig functions or some type of crazy elaborate thing, it may be very difficult to figure out what the inverse would be. And so we have a two-step process that we can use to create the inverse of a function. Step number 1, we're going to switch x and y, and then step number 2, we're going to solve for y. So for our equation here, we've got f of x equals x cubed plus 2. Where's y?
F of x.
It's f of x, right. So you could rewrite that as y equals x cubed plus 2. So then step number 1, we're going to switch x and y. Okay? So we've switched x and y. And then step number 2, we're going to solve for y. So how do I get y by itself? Subtract 2 and then take the cube root. So it's exactly what we thought it would be, but we may have been unsure about the order or had a more elaborate equation than what we've got here. All right, now let's talk about the graphs of equations and their inverses. You might remember that the graph of a function and its inverse are always going to reflect each other in the line y equals x. So the line y equals x is this little dotted line right here. It goes through 0, 0, 1, 1, 2, 2, -1, -1, Okay, we're going to reflect our inverse and reflect our function across that line. So it wouldn't matter if they gave me the original function or if they gave me the inverse. I could reflect it across that line either way. Now, there's some of you that you're very visual people, so if they give me this function and they say this is f of x, graph the inverse, you're not going to have any trouble with reflecting that across that line. There are others of you that would be more difficult. So remember we said that the ordered pair on the original gets flipped for the inverse, right? Here's what I could do. I could identify for myself as many points as I needed. Like I could come over here and say, okay, this is the point 3, 0. So if it's 3, 0 on the original, what is it on the inverse? 0, 3, right. I could come down here and say if this is 0, negative 2 on the original, what is it on the inverse? And I could do that as many times as I needed to kind of give myself some guide points to then come over here and draw this. So if you needed some more points in here and some more points in here, give yourself as many as you need to help you sketch that. And it doesn't have to be perfect as long as I can see you know what you're talking about. All right, so now we're finally to some calculus. Over in the middle of 411, they talk to us about the calculus of inverse functions, and they give us a couple of theorems. It says, first off, if f is a one-to-one continuous function defined on an interval, then its inverse function is also continuous. Here's an easy way to think of this. If you can draw this original function without picking up your pen or pencil, it's continuous, right? If you reflect that across something, isn't that still going to be a drawing that you could draw without picking up your pen or pencil? That's not going to change, right? So that makes sense what they're telling us there on the middle of 411. And then over on the top of page 412, they give us another theorem, and it says, if your function is a one-to-one differentiable function with an inverse function g, that's the inverse of f, then the derivative of f of g of a is not equal to 0, then the inverse function is differentiable at a and can be found by this formula that you see right here. We're going to use that formula to find the derivative of the inverse at a particular value. Okay, so look at example number 6. For example number 6, they give us a function, f of x is equal to x squared. Now, if they gave me that whole parabola, I'd have problems, right? Because it wouldn't pass a horizontal line test, and so I wouldn't have a one-to-one function. So you'll notice that they're restricting the domain. We're only interested in the piece between 0 and 2. All right, a couple of things about that. If we're talking about restricting the domain, let's think about the domain and the range for these. What's the domain for the original function f of x? 0 to 2, right. What's the range? 0 to 4. If I want the domain and the range for the inverse, what's the relationship between domain and range for original versus inverse? They just switch, right, because if x and y switch places, domain and range switch places. So when I know the domain and the range of the original, like you just told me, all I have to do is switch them to know the domain and the range for my inverse. I didn't have to graph the inverse to get that, right? I could. There's no reason why I couldn't draw my line y equals x and reflect it, but I don't have to do that to know my domain and range. So when I'm coming down here and I'm trying to find some values, it would be helpful if I'm trying to find values of the inverse if I kind of have an idea of what I'm working with before I start. Okay, so they asked me in example number 6 to find the derivative of the inverse at 4. So if this is the formula they gave me for the derivative of the inverse, I'm just going to put 4 in the place of that a. So I'll come over here and put 4 in the place of a. So let's start down here on the inside with g of 4. I need to know what g of 4 is equal to. Okay, well, I don't even know what g of x is, so how am I supposed to plug 4 into it if I don't know what it is? I don't have to. If I'm looking for the ordered pair 4 question mark on the inverse, what is that on the original function? If I'm looking for the ordered pair 4 question mark on the inverse, what is that ordered pair on the original? Question mark 4, right? So all I have to do is set my original function equal to 4 and solve, and I'll know what that value is, right? And once I know what x is over here, that'll be the y over here. So let me say that one more time because that's really the key to this whole thing. If there's a tricky part to it, that's it. When I start down here, I need to know g of 4. That means I need to know when x is equal to 4 on the inverse, what's the y value, okay? So if I have 4 and some unknown y value on my inverse function, when you switch x and y for the original, that would be an unknown x value and a known y value of 4. So I could say, okay, if I set my function equal to 4 and solve, that would give me this x value. If I know the x value on the original, that will be the y value on the inverse. Okay? So let's take our original function and set it equal to 4. So we had x squared is equal to 4. Take the square root of both sides and we'll get plus or minus 2. If I go back and I think about the domain of that original function, it was only valid from 0 to 2, right? So for that reason, I can eliminate the negative 2, and I'm just going to use the positive 2. So if I have the ordered pair 2, 4 on the original, then that has to be the ordered pair 4, 2 on the inverse. If I didn't catch the plus or minus 2 down here, remember that we've already figured out what the range should be on the inverse. So if I came over here and I was trying to say this was a positive 2 and a negative 2, I could catch it right here on the range of that inverse that I should only be using the positive and not the negative. Okay, so now I know that g of 4 is equal to 2. Now you'll notice everything else I need to know just deals with the original function, not the inverse. So I can go through. I need to know the derivative of f at 2. So here's f of x up here. What's its derivative? 2x, right. So if I know that the derivative is 2x, then I can put 2 into it, and 2 times 2 would give me 4. So I'll replace the derivative at 2 with 4, and I've got 1/4. So the derivative of the inverse at 4 is 1/4. Here's what's so amazing about this. We just found the derivative of the inverse at a value, but we never found the inverse function, nor took its derivative, nor plugged a number into it. So that's the power of this formula. Now, they intentionally chose a really easy equation for us because they want us to be able to verify that this formula really does work. And so here's what they say. Now we want you to redo that problem a different way. We want you to actually find the inverse, take its derivative, and plug 4 into it and see that you get the same thing. Okay, so let's do that. We've got x squared, so what would the inverse of x squared be? Square root of x, right. So if my inverse is square root of x, or maybe you want to write that as x to the 1/2, what would the derivative of that be?
1/2 x to the negative 1/2.
Yes, 1/2 x to the negative 1/2. And so then all we need to do, if we're trying to find the derivative of that at 4, let's just go through and put 4 in the place of that x right there. So that would be 1/2 times 4 to the negative 1/2. So we'll put 4 under the radical in the denominator. And so we'll get 1/2 times 1/2, or 1/4. So I get the exact same answer. So you look at that and go, well, what do I need that formula for then? If I can just do that, I mean, that was a whole lot simpler to actually write the inverse and take its derivative and plug in a number. Okay, well, look at example number 7. I get down to example number 7, and I've got f of x is equal to 2x plus cosine x, and they want me to find the derivative of the inverse at 1. I don't even want to find the inverse of this thing. Because look, if I've got y is equal to 2x plus cosine x, if I try switching x and y, then that's going to be x is equal to 2y plus cosine y. How are you going to get y by itself? You're going to have to do inverse cosine, and then you've still got another y to have to deal with. You're going to create an equation that is a monster, and then you're going to try and take the derivative of that. I don't want to have to do that. If I could just work with the equation I already have, then that would be great. So that's what I want to do. I'm going to go back and use this formula that they gave us right here. So I want to find the derivative of the inverse at 1. So I'm going to plug 1 into my formula. All right, so when I plug in 1, let's start with g of 1. So again, it's that same thought we were talking about before, where if I need to know the inverse at 1, because that's g, the inverse, if I need to know the inverse at 1, that's 1 question mark. Then in the original function, that would be question mark 1, right? If I want to know 1 question mark on the inverse, that would be question mark 1 on the original. So all I have to do is set my original function equal to 1 and solve. All right, so let's do that. Let's take the original function, 2x plus cosine x, and set it equal to 1. And I'm going to do that on my calculator. So grab your graphing calculator if you would. All right, so we've got 2x plus cosine x is equal to 1. First off, what mode do we need to be in? Radian. So check and make sure that you are in radian mode. How am I going to find that on my calculator where those two are equal to each other?
2x and then cosine x and then intersection.
Okay, so I'm going to put what's in the left-hand side of the equation in y1. And I'm going to put what's in the right-hand side of the equation in y2. You can do whatever zoom you want to. Typically, when I'm working with the trig function, I do a zoom 7, a zoom trig, but you could do whatever you wanted to. So there's 2x plus cosine x, and there's y equals 1. And it looks pretty obvious that their point of intersection is at 0, 1, but I could just double check that. So second trace, which is my calculate menu, option number 5, intersect. And it's asking me, do you want me to use what you've got in y1 for your first curve? So enter for yes. Do you want me to use what's in y2 for your second curve? Enter for yes. And come over here as close to we get to that point of intersection, and sure enough, it verifies for me that that intersection is 0, 1. So we put left-hand side in y1, right-hand side in y2. We went to zoom trig, and we asked it to find the intersection, and that point of intersection was at 0, 1. So once I know that I have the ordered pair 0, 1 on the original function, then that would be 1, 0 on the inverse function, right? So I can come down here then and say, okay, g of 1 is equal to 0. So now I have the derivative of f at 0. So let's go back to f of x, and we're going to need its derivative. So what's the derivative of 2x plus cosine x? 2 minus sine x, exactly. And then we can put 0, because we need the derivative at 0. So let's put 0 in for x, so that would be 2 minus sine 0. Sine at 0, of course, is 0, so 2 minus 0 would give us 2. So the derivative at 0 is 2. So once again, we were able to find the derivative of the inverse at a value. We never found the inverse, never took its derivative, and plugged a value into it. So that's what that formula allows us to do. Now, one of the kind of requirements for this theorem, it says if your function is a one-to-one differentiable function with an inverse, and the denominator, of course, is not equal to 0. So something that would help us with this in terms of making sure that this is a one-to-one function, you know, if I don't have access to a graphing calculator like I don't on half of my AP exam, how can I tell without graphing this thing that it passes a horizontal and vertical line test? Well, what would help me here is the fact that the derivative is 2 minus sine x. What is the largest value that sine can be? 1. So if I do 2 minus 1, I still get 1. That means whatever value I put in for sine, I'm still going to get a positive value for that derivative. So if that entire derivative is greater than 0, anywhere the derivative is greater than 0, the function is increasing. So that means this entire function is increasing. If you did a horizontal vertical line test on that, you would be fine. So that would be a way to know that it's one-to-one without having to look at the graph. Now, one last thing that they give us is example number 8, and we're doing this whole thing on the calculator is why it's not listed there on your note sheet. For example number 8, it says show that the function f of x is equal to the square root of x cubed plus x squared plus x plus 1 is 1 to 1, and graph both the original and the inverse. And they have us using our graphing calculator to do this. Now, the way that they do it in the textbook is they redefine these with parametric equations, and you definitely could do that. But if I have my graphing calculator, there's a much simpler way to do this on my graphing calculator. I can graph the original function, and I can tell my calculator to draw the inverse for me. I showed you this last year at the end of pre-cal, but it's been a little while, so let's go do that again. So first off, we want to go to y equals and put in our new equation. So let me clear out what we've got in here. So we'll go to y equals and we'll put in that equation that we just have. So we just had, that was the square root of x cubed plus x squared. Oh, I didn't like my x apparently. Now it's going to give me two of them. It's temperamental sometimes. All right, now we're back on track. X cubed plus x squared plus x plus 1. And I'm going to graph. And if you'd like a larger view of that, you could also go to a zoom 6, whatever you prefer. I typically start with a zoom 6, and then if I want a closer view, then I go to a zoom 4. So whatever window you're comfortable with, we'll go with this guy so we can see it a little bit better. All right, so I've got the equation in y1. If I'll go to second program, which is draw right there, so second program, I'm going to go down to draw the inverse. So down there to number 8 is draw inverse. And I have to tell it what I want it to draw the inverse of. So I'm going to tell it to draw the inverse of what I have in y1. You also could retype the whole equation here, but why? So if I tell it to draw the inverse of what's in y1, isn't that happy? I love that. So, you know, there's no reason why we couldn't reflect it across the line y equals x, but I think that's kind of cool that when we have the equation, we can get our calculator to draw it for us. All right, so once again, we just put the equation in y equals, and it graphed it. And then we went to second program, which was draw, and went down to draw inverse. Told it to draw the inverse of what we had in y1, and it generated it for us. Okay, so here is our homework for tonight on pages 414 to 415. We're doing 1 through 11 odd, 21, 22, 25, 31, 35, 39, 43, and challenge 45, but use that draw inverse instead of the parametric equations to play around with 45.